Hello everyone. Have you ever tried to open a door by pushing at its hinge? It hardly moves. But push at the edge, and suddenly the door swings easily. That turning effect comes from torque, and torque is defined using the vector product. The vector product, or cross product, takes two vectors, say A and B, and produces a third vector C. Its magnitude equals a times b times sine theta, where theta is the angle between them. And most interestingly, the result is not in the plane of A and B, but perpendicular to it. That's what makes it so powerful in rotational physics.
To know the direction of this new vector, we use the right-hand rules. Imagine holding a right-handed screw flat against the plane of vectors A and B. If you turn the screw head from A towards B, the tip moves in the direction of C. That's called the screw rule. Alternatively, curl the fingers of your right hand from A to B. Your extended thumb now points in the direction of C. But be careful, always rotate through the smaller angle between the vectors, less than 180 degrees. Otherwise, you'll end up pointing the wrong way.
Now let's explore its mathematical behavior. The cross product is not commutative. That means a cross B equals negative of B cross A, same size but pointing in the opposite direction. If you take a cross with itself, you get 0 since sine 0 is 0. It is distributive though. A cross open bracket B plus C close bracket equals a cross B plus a cross C. And under reflection, the cross product does not change sign even though the individual vectors flip. That's why it's called a pseudovector. Remember the dot product? That gave us a scalar, a dot B equals AB cos theta. It measured how much two vectors line up. The cross product, on the other hand, gives a vector, a cross B equals AB sine theta in the direction of n hat, which is perpendicular to the plane. The dot product is commutative, a dot B equals B dot A. But the cross product is anti-commutative, a cross B equals minus B cross A. Both share one thing though, they distribute over addition. Together, dot and cross products form the backbone of vector algebra in physics. Let's derive the component form. Suppose vector A equals AX I hat plus AY J hat plus AZ K hat. Similarly, vector B equals Bx I hat plus By J hat plus Bz K hat. Expand their cross product term by term using rules like I cross J equals K, J cross K equals I, and K cross I equals J. Collecting terms gives a cross B equals open bracket AY BZ minus AZ BY close bracket I hat plus open bracket AZ BX minus AX BZ close bracket J hat plus open bracket AX BY minus AY BX close bracket K hat. Compactly, this is written as the determinant with I hat, J hat, K hat in the first row, AX, AY, AZ in the second, and BX, BY, BZ in the third. This determinant form makes calculations quick and elegant. Give its proper voiceover. Why do we care about the cross product? Because nature is full of it. Torque is our cross F, the turning effect of a force applied at a distance. Angular momentum is our cross P, how mass in motion contributes to rotation. And in electromagnetism, the magnetic force on a charge is Q times V cross B. Notice the common theme. The result is always perpendicular to the original vectors. That's why the cross product is indispensable for describing rotational and magnetic effects.
So to summarize, the vector product gives us a vector whose magnitude is a b sine theta and whose direction is perpendicular to both original vectors. Its orientation is fixed by the right-hand rule. It is anti-commutative, distributive, and vanishes if the vectors are parallel. The determinant form makes computation straightforward. Most importantly, it underpins torque, angular momentum, and magnetic force, the very pillars of rotational dynamics and electromagnetism. I hope you now see why the cross product is not just algebra, but a language of rotation and force in physics. See you in the next session, where we'll extend this further into rotational motion.